Section 11.6, Archimedes Principle. Now this principle is all about the idea, if you've ever taken a beach ball to the pool or to the ocean, if you try and push that beach ball underwater, you feel there's a huge amount of force pushing back. That beach ball does not want to go underwater. That's known as the buoyant force. So how do we know what the buoyant force is? Well, the buoyant force has to do with all of the water pressure around the object. So if we imagine submerging an object underwater, so it could be a cylinder, beach ball is pretty hard to get underwater, could be a block, whatever you'd like. We're going to compare the forces, the force coming from the pressure above, pushing down, and the pressure below. There's more pressure below, as we've seen before. And so the net force is an upward force, this buoyant force. So we note the buoyant force with this F sub B. And so the buoyant force is equal to the difference in the two forces. So force 2 going up minus force 1 going down. Then we could pull the area out of that, right? So it's pressure 2 minus pressure 1 times the area. We've already seen pressure 2 minus pressure 1. That's our gauge pressure. The difference between two pressures is a function of depth. So it's equal to rho GH. So we can plug in rho GH for those parentheses. But we can also note we have H times A, and that's what we figured out was our volume. So we can instead write this as density times volume times G. But density times volume is mass. And it's just going to be what? Is it the mass of the object? Not quite, because remember this is the density of the fluid. So the density of the fluid times the volume of the object, if the object's completely underwater. In other words, the volume of the displaced fluid. So this is the mass of the displaced fluid. And this is going to be the key to calculating our buoyant force. That's what Archimedes' principle is. So Archimedes' principle says that any fluid applies a buoyant force to an object that is partially or completely immersed in that fluid. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. So here's the equation written out in formal terms. Buoyant force magnitude is equal to the weight of the displaced fluid, not the weight of the object, the displaced fluid. So we can often write this in terms of, as on the previous slide, the density of the fluid times the volume that is displaced times G. This is a really handy equation to be able to calculate the buoyant force. Now there's one other trick to figuring out the buoyant force. We have a special case buoyant force. That's if the object is floating, then we know that the buoyant force is equal to the magnitude of the object's weight. This is only if the object is floating. Archimedes' principle always applies. The buoyant force is equal to the weight of the displaced fluid. But if it is also floating, then we can say that our buoyant force, F sub B, is equal to the weight of the object. And we can see this if we imagine, like, if we're lowering a block into the water, right? Then it has some weight, say 100 newtons. As we initially put it in, it's only displacing a small amount of water, right? That depends on however much volume is submerged. So it may not be enough that they balance out. The object will keep sinking. But there may be a point where enough water is displaced when it goes deep enough that the object is able to float. And if it is floating, we know that the downward and the upward forces need to balance. So the weight of the object is exactly equal to the buoyant force. If the buoyant force was greater, the object would be accelerating upward, right? That's what happens with the beach ball. It exerts a huge amount of buoyant force because the beach ball displaces so much more water than the beach ball's weight. If you have something that is larger than the buoyant force, then it's going to accelerate downward. It's going to sink to the bottom of the water. So floating is a really special in-between case. And we're going to see an example of floating with a raft in the next video. But before we get to that, I do want to highlight a couple of other examples of Archimedes' principle in action. So this conceptual example 10, how much water is needed to float a ship? A ship floating in the ocean is a familiar sight, but is all the water really necessary? Can an ocean vessel float in the amount of water that the swimming pool contains? And it turns out you don't need all that water. You don't need an entire ocean to float a ship. All that you need is just enough water to separate the wall from the canal bottom and sides. So that could be the amount of water in a swimming pool, because you're able to displace enough water to support the weight of the ship, so the ship can float. And this is actually used in principle. So I had a student bring up this example, I believe this is in Scotland. There are all these canals that have ferry boats that go along them, but sometimes you need to go from one height to another height, and you can't just take an off-ramp with the canal, right? But there's this lifting system that actually the boat goes into it, and then the whole segment rotates around, either down or up, and the boat is floating in not that much water, right? This is not that big of a thing, but the boat's totally fine. So the boat is still floating, even in this tiny contraption. So you can check that video out and see it in action, to see it with your own eyes, that this does in fact work. One other application of Archimedes' principle is large batteries like car batteries often will have an indicator to say, hey, what's the state of the charge? And if it's good, then maybe there's a green dot there. What's actually behind that green dot? What makes the green dot turn black when the battery is no longer good? Well, the key is that there's a little plastic ball, right, that's held in this cage, and it's floating because of the density of the battery acid, right? We know that the buoyant force is equal to the weight of the displaced fluid. So it's equal to that density of the fluid, which in this case would be the density of the acid, battery acid, times the volume that is displaced, which would just be the volume of the ball, times G. So guess what? As time passes, the battery acid's density drops. It starts to lose its charge. So as that drops, the buoyant force is also going to drop. And eventually, the ball is no longer able to be supported by the buoyant force, as the ball falls down to one of these sides. And now if you look down the indicator, you no longer see a little green dot. You just see a black dot, because the density of the battery acid is not enough to keep that little green ball afloat. So there we have it, another application of Archimedes' principle in action.